meeting is an overview of some of the activities of Velev groups over quite a few years related to different types of coatings, organizing particles, the type of materials. Our present work is in other topics to some extent, but it is grounded in this field. And I would like to present the background of Velev group research in this area. This is a summary slide from a few years ago. Some of the beautiful structures that we have made in Velev group. You can have the organized particles, which is one of the original topics. This is a coating made out of viruses. Then you have the so-called inverse metal Opal materials, different types of special particles. All of those structures have beautiful, many cases, they have beautiful optical properties, beautiful covers, as you can see here. And those beautiful covers come because of the organization of the particles. So what I'm going to do in this talk is I'm going to present some of our earlier research, and starting from there, I'm going to use this as a way of illustrating how do we calculate the optical properties of those structures, right? You see those structures, they have very nice covers, but where are those covers coming from? And how do you correlate the structure to the cover? Why I'm saying correlate the structure to the cover? You may have heard the terminology of structural cover. So structural covers means that the cover that you're seeing here does not arise from any physical absorption of light. It comes from the interaction of the light with the structure that we have here. One of the original topics that have fascinated many people over many years is the organization of simple spherical particles in the so-called colloidal crystals. This has been a topic that was a good topic, considered to be a hot topic when I was a graduate student. There are still quite a few groups worldwide who are working in the topic of making particle structures. This image, actually, out of all the images that I'm showing, this one is not an image from our group. This is a beautiful image from the work of one of my friends and early investigators in this area. You may have heard the name of Nanocoating, a very famous guy in this area. So he has organized those nice microspheres. We have done this quite a few times also. They look beautiful when you use microscope, electronic microscope. They look beautiful when you look at them just in regular illumination, because they have cover. And why do they have cover? Well, the covers in this case, and that you have heard this kind of going around, especially our group for quite a few times, about the Opal type of structures, right? Opals are type of natural colloidal crystals that have assembled in certain conditions over, I kind of presume, hundreds and thousands of years, and have formed this beautiful structure. So people have always been fascinating why an opal is going to have this. Well, the word for the covers of the opals is called opalescence. So why would opals are going to have this type of beautiful cover? So you can see that, like, I mean, many years ago, essentially one of the biggest discoveries has been that this cover is a structural cover. So if you take an opal and if you cut across it, then you're going to see essentially what I just showed you on the previous slide. You're going to see three-dimensional organization of microspheres, that is submicrospheres, in the colloidal crystal. Obviously, the covers come from, again, the structure here. This has been considered to be a big discovery for its time. I mean, still the journal Nature has been the top journal at that time also, of course. So since then, people have been making opals artificially by actually making silica particles and then sintering the silica particles in this way. For all I know, naturally, these particles have formed by very slow precipitation of silica in natural cavities in oversaturated water, and then those particles have settled to form beautiful natural opals. We want to discuss now where this comes from, and one of the phenomena that is very important in this case is called diffraction, and the equation that describes this diffraction, the so-called Bragg equation, has been derived many years ago when people have been studying X-ray reflection from crystals. So originally, so you can have the same type of phenomena if you go to much smaller scale, you take a molecular crystal, you shine X-ray, which has the right wavelength, and then you have the same phenomenon. So what happens here is you have a beam. It comes from a certain angle, and then it gets reflected at the same angle. What happens is that if we have a beam being reflected from this layer of spheres, and if we have another beam which is reflected from this layer of spheres, you can say, oh, this is the same light. But the two light beams that you are seeing here have traveled a different distance. So this one has traveled a shorter distance than this one, which has gone down to the layer below and then has gone up. So in that regard, you can say, okay, so what is the difference? If you are considering a single beam, you're not going to see any difference because the difference is in the so-called phase of the light. So if the two beams have the same organization of the wavelengths, then during the reflection, you're going to have this beam traveling this additional difference. So when they emerge, the wavelengths, which may have been originally synchronized, are going to become dissynchronized. So now, depending on how those wavelengths stack up, you're going to have the phenomena of positive or negative interference. And essentially, these two beams are going to either enhance each other or are going to cancel each other. It's kind of a little bit of unintuitive in the sense that how can light cancel each other, cancel itself? But this is what happens if you take two beams of light and if you change the phase of one of those beams. So when you put them to overlap, so one is going up, the other one is going down, essentially like here. The sum of those two wavelengths is zero, so the light cancels out. There is a Bragg equation, which is very useful, and it's kind of like in many cases describes the properties of similar structures. So this equation has been used by us, by many other people. I'm going to go back to it when we're discussing thin films. But kind of like, so please keep in mind what you're seeing here, and then you tell me the difference in the case of films. So now we want to form crystals. In the original work, in my case and in the case of many other people, has been making those three-dimensional. So people won't say, okay, well, I want to make it three-dimensional. How do we make that? Well, answer is very easy. Simplest way to make a three-dimensional crystal is to take the suspension of latex spheres. You know that we have some in our laboratory. Only thing that kind of makes them monodisperse is the strict operation in the by producer specification, and not very cheap, but I mean, of course, they are easy to obtain. You can have latex spheres, you can have silica spheres, you can sediment them, let them go down by gravity, you can use centrifugation, you can use filtration, which I have done when I was making such spheres at one point. You can use electrical fields in the original implementation. This is not the more complex type of electrical fields that we're using. So now we have those spheres. I mean, the properties of the spheres are described here. I'm not going to go into too many details. You can think of this as, okay, you can say, okay, so now I have a nice material. What can I use it for? The answer is the following. If you make it out of spheres in three-dimensional case, it is a nice, beautiful, powdery, colored powder, right? I mean, it looks nice, but it is not self-sustained. I mean, it's going to be made in the form of flakes, and those flakes are going to be pretty shaky. They'll be breaking out easily. So you want to convert them into a material. So one of the things that I did myself personally, just for fun, as a side project, as a postdoc at the University of Delaware, was come up with the first idea and the first description of what was later called inverse opals. Essentially, you can take a crystal of those spheres, latex. You can infuse it with silica. The silica can relatively easily then be polymerized and calcined. So then you put that into an oven, into a furnace, and what comes out is this very nice, beautiful material. So as a postdoc, I was kind of the initiator of this work, wrote that paper, published it into Nature. It was at one point the most cited paper from the University of the Chemical Engineering Department, University of Delaware, just because people were so very interested in this type of materials. And this was partially kind of like, I mean, the way of kind of like making academic impact. you can make those materials out of silica, and then you can make those materials out of metal. Making them out of metal was at that time also another challenge because, okay, silica, I mean, you polymerize the silica, I mean, calcine it, fine. I mean, you have like solid silica. How do you make a metal? So there were some folks, mostly physicists, who were trying to do it the kind of the direct way, which is you melt a metal and try to infuse a crystal out of silica, for example. Those of you who have taken my class know that this is not going to be easy, because of the very high capillary pressure that you need to apply in order to infuse the crystal with the metal. What I did later on, I came up with this, I would say, shortcut, which is if you take metal nanoparticles and if you infuse the large crystals with the metal nanoparticles, so now you're going to have the crystal from the polymer spheres surrounded by gold nanoparticles. In this case, you can actually, if you heat up this crystal a little bit, you're not only going to calcine that is remove the spheres, but you're also going to fuse the particles into continuous metal. So at that time, this was another paper in Nature where you have those beautiful gold flakes with covers. So how do you make gold flake with a cover? Well, I mean, you make it into inverse opal out of gold. So that was another kind of another way of showing up how the whole thing was out. This was the background with regards to materials, and then I'm going to be switching to coatings very soon. But let's kind of like stop here and get some questions, maybe. Anybody? Anything on the historical perspective here? Okay. I kind of like, I mean, please think about participating like in the next few kind of slides. Let me, actually, maybe it will be easier for me and for you to, if I'm sitting down and kind of taking it a little bit kind of less formal. So now you have this material. The question is, what can you make out of it? Well, a flake is not really something that is extremely useful as it is. Well, you have it, I mean, it's beautiful. It may be used in something like adsorption, but if you want to make more type of organized and structured materials, what do you do with something like that? How do you organize it in something more structured? What is the simplest way of really having material properties on the micro scale in a tangible way? What do you make out of it? Very simple. Like what? What is, let's say, if we have some material and you want to investigate it without having to investigate some powder, what do you make out of it? How do you convert it to something useful and simple?
A coating?
Colloidal suspension.
Yeah. Coating is good. Sorry, was it Lillian also suggested something, or?
Yeah, colloidal suspension out of it.
Suspension is good. So you can, let's say, you can make two things. And that's a very good introduction to what I'll be mentioning in the next slides, right? So you can either take that material and spread it very thinly and uniformly and keep the organization and actually control the organization, or you can say, okay, I'm going to make larger particles out of it, and I'm going to investigate those particles. I will show you how we have done both of those things, really. So how do you make a coating? This goes back to my my PhD thesis and actually my first paper, even though that was not on my PhD thesis. So what was my PhD thesis about? Let's see who knows. It was not about colloidal crystals, let me tell you like that. So I came from a very well-known Bulgaria group, internationally known, mostly fundamental work, kind of really fundamentals at their best. But what was my graduate research about and my graduate thesis? Let's see who knows his or her boss. What was the topic? Guesses? Among
Coffee ring formation, or like?
Well, Well, coffee information relates to organization of particles also, right? So I'm saying, no, it wasn't about the organization of particles. What was it about? It's something else, colloidal.
Is that when you did the protein and light scattering work?
No, that was my postdoc work at the University of Delaware.
Yeah.
So what was my graduate thesis about?
Wasn't convective assembly.
Another bunch of colloidal systems that we have been discussing that we're using. What other systems can you think of? And what we have we been investigating in some other projects?
I know you supervised someone. Was it when you were a postdoc that you supervised someone with the xylene dispersion in water?
Yes, xylene dispersion in water is good, right? But xylene dispersion in water is going to be called
emulsion.
Yeah, so it was. So my graduate thesis actually was on foam and emulsion stability.
Ah.
So those of you who have foams or emulsions kind of can say, oh, you know, we're going back to the basics, right? I was interested in some kind of new, more high-tech systems. And at that time, my professor started collaborating with a professor in Japan called Kuniaki Nagayama, who was interested. So kind of like, I mean, he was not a colloidal guy, but he was very much a visionary guy. And he was foreseeing that colloidal crystals with their unique properties are going to become kind of a material of the future. And research-wise, they really did. Kind of like the beautiful colors were emphasized so much. You know, as I told you, this is kind of the story of over and over, right? I mean, periodically, every about 3-4 years, I see some press releases, some new professor, kind of typical young professor, say, oh, you know, I discovered something beautiful. If you organize particles, they look like opals, or if you organize particles, they look like the wings of the so-called morpho butterfly. They're beautiful butterflies that have beautiful wings. So for me, this is kind of, you know, like Back to the Future, because I have heard that story so many times from so many professors who were young at that time, and then kind of, so like, I mean, essentially academics tend to rediscover things and be fascinated by it. But this has been one of the fascinating systems. This was fascinated the Japanese professor. I was kind of like looking to do something on the side, so I started working with my colleague, and then we designed the first experiment to discover what was now known as convective assembly. So this is what happens at the periphery of a droplet, the so-called coffee ring. This is what you can do to organize particles. So this is a photo from our paper at that time in Nature. What you can see here, and again, you can see that all those papers were very simple stuff based on new ideas, which at the time people had no idea about. So that's why, you know, those of you who kind of want to train their brain to kind of come up with something new, you can see that you don't have to come up with something extremely complex to make some good research, right? I mean, it just has to be new and original. So hopefully that's a kind of a little bit on the side, something to keep in mind. So this is a photo from not my graduate thesis, actually, it went into the thesis of my colleague, but I was kind of the main experimentalist there. You can see the particles in a two-dimensional crystal that has been organized in the surface. Essentially, you have the liquid evaporating here, drawing particles in. When these particles organize, they form the colloidal crystal in a very thin layer. So essentially, we have a coating of colloidal crystal. The evaporation keeps sucking liquid with the particles. Essentially, for the liquid that evaporates here, and some of you will tell me why, you're going to have a flux that is going to be drawn in here. What creates the pressure for the flux to come into the crystal? It's very simple. This will be the
Is this the Marangoni effect?
Yeah, I did not hear what effect you mentioned.
The Marangoni effect? I may not be.
Marangoni effect would be if you put surfactant, in which case the whole thing kind of gets messy. But then I think even simpler, which relates to what I'm showing here. I think was saying that.
Capillary.
Capillary is a good stuff, right? You can never go wrong with capillary stuff, as Lillian knows. So essentially, the capillary pressure would create, if you start evaporating liquid from a crystal, you're going to have the meniscus here is going to go below the surface of the beads. And when it goes, you're going to have essentially a negative pressure because of this high curvature. And then it is going to be drawing new liquid from the meniscus. So this under pressure in this case is capillary pressure. We're using it in new type of materials for 3D printing these days. In this case, this is what drives the liquid to go in there. When we were writing, one of my bosses who was doing theoretical work, Professor Peter Kauchevsky, you may have heard his name. He was actually the chairman of the European Colloids Society for a while. Was very interested in capillary forces. So we mentioned that capillary forces are important, which happen when you have particles on the surface. And they will be important, but only for a monolayer. So if you have a monolayer, it is very hard to dry, which I kind of constantly get those questions from industry, right? Why, when you dry suspension of particles, they do not disperse uniformly, but they form ions. They form ions because when you dry particles, at the final stage of drying, particles which are close by will be drawn by the capillary forces, in this case, will be drawn together, so they will stick together. This is only for a monolayer. For a multi-layer, essentially, you are going to have this evaporation taking place, and the particles would remain, the liquid is going to leave. So this is how you deposit a layer. This is how you make coatings in general, if you think about it. But in this case, the difference is that the coating is made in a way, so the liquid that gets drawn in is going to be bringing the particles. So you essentially have a moving front. You do not dry it like that, you draw it at a moving front. And because you do that, you can organize the particles very well, and you can have the, the colloidal crystals, the beautiful color and everything. So at that time, what was described at that time is essentially that you can do a balance, and you can say the evaporation flux is going to be correlated to the number of particles in the meniscus. And the faster you evaporate, the more particles you bring here. But we did not kind of do this in an engineered way. We just described the phenomenon. So this was the background of the two-dimensional assembly. Again, that goes back to my graduate work, but that was not my thesis, but kind of like some fun work that I was doing on the side. Then I went to Delaware. I have been working on protein crystallization. I did the side work on the inverse Opals. Then I started as a faculty here. I got my first two PhD students who were, what was the name of the first two PhD students? You may have heard of Brian Prevo and Kevin Butt. So these were the guys who kind of like were really kind of very entrepreneurial in many aspects. Research, presentations, free food in the department. I mean, they were kind of, they were really kind of very cool guys. And we did lots of work together, like you're cool guys now, doing lots of work now. So what we started doing with Brian, so I have heard by then so many times the story about the morpho butterfly wings and people noticing that and so on, and nobody had actually engineered the process. So with Brian, we decided just for fun, we're going to start engineering it, right? We're going to make this in a way where we write the formula the other way, right? What can we achieve if we control the process? So what Brian did was something, and kind of like, one of those devices, at least one of those devices still going around. We made another one later. I'm joking, the high-tech deposition device. I'm sure that you're familiar with the modified syringe pump, which you use to deposit particles around. There were two of those. I hope there's still the two of them are still around, but at least one is kind of like prominent.
Two.
Uh-huh.
We still have two.
Yeah. They look a little bit beaten up, as you may have noticed, but this is because they have been used so much. So we have used them to deposit practically any particle or any surface. Originally, we were working with latex. It's a very simple idea and a very simple device. Yet kind of like, so this paper by now has hundreds and hundreds of citations. Just because, again, like, if you do something like that and if you do it well and explain it to people, people like it. I hope your papers are going to have similar impact now. So essentially, you put a droplet with the droplet here. It forms a so-called meniscus. This is the curvy liquid. And when you drag the top plate, you are going to be essentially dragging this meniscus with a certain rate. you would imagine that the fastest you draw this meniscus, the less particles will be deposited behind, because you have evaporation here, but this evaporation can take place in as much as kind of how many particles you let go there. The velocity of withdrawal of the meniscus is going to control the deposition rate. So that was kind of like the basic premise of this work. And then we started investigating what would be the conditions for depositing different layers of different thickness by just using this simple device. And we found out that kind of like we can control this pretty well. Before anything else, what is the type of structure that is formed here, kind of like looking at the image here, and can it vary? Some of you may have encountered that at one point or another. What is the name of this type of structure? Single layer crystal.
Hexagonal close packed.
This will be hexagonal close packed. Great. Can you have some other type of structure that's hexagonal or not? Why is it hexagonal?
Because the particles are spherical. So when they're packed together, they make a hexagonal structure.
Aha. So when you pack particles, the kind of the highest efficiency of packing is you obtain it when they're hexagonal, right? Can you obtain another structure in this type of deposition or not? If you don't know the answer, maybe I should show you. This is again from the original definition of this in geometrical sense was kind of has been done years ago. But essentially, what Bragg described, and this is a photo from his paper, is the following: that if you have a thickness here, so if you, let's say, organize a layer of water, if the thickness of the layer is just one layer, one particle layer, then the particles kind of squish in there. They organize hexagonally. If you increase the thickness a little bit, actually, at a certain point, you're going to have the hexagonal bilayer. But if your thickness is intermediate, so you would imagine that if you want to pack, how do you pack particles in a thinner layer than bilayer, hexagonal bilayer? Or you can see that if you have one particle residing between four others, it is going to go lower, right? So the thickness of this kind of like square lattice is going to be smaller than this hexagonal lattice. So essentially what happens here is that if you draw slowly and if you control the thickness here by your drawing, you're going to go through a transition of hexagonal monolayer, square bilayer, hexagonal bilayer, square trilayer, and then hexagonal trilayer, and so on, right? So you can see those structures as the thickness varies. Nature does this because this is how the particles like. Any questions here? Comments?
I have a question about the previous slide, actually. No, it's not on the structure that you can produce. I'm just curious, what is the plate made of? So is that like a metal plate? Is that a glass slide? Or what is that actually made of?
Oh, this is just, so all that you have here is two glass slides, right? So this is, the beauty of this setup is how simple it is, right? So essentially, now you have to watch the slide or functional, right? So you take a simple glass slide, put it on the modified syringe pump. You have another glass slide from the top, and then you drag it along the first one. Now, there is an engineering trick here. You have to make this slide. So if you try to very tightly fix the slide like that, and then if you try to drag it exactly very precisely yourself, you cannot do that, right? You're speaking a very thin meniscus, your slides are, there is always going to be some misalignment and so on, so the whole thing kind of like becomes kind of screwed up very easily. So the simplest way to do that is actually have a flexible link here. So then when you put that slide, it just resides on the top of the other one, and then it self-aligns and drags along the top of the bottom slide. So there is this dirty, by now, piece of transparency. For those of you who have ever known what the transparency is, which is actually used to create this flexible link to drag the top surface with regard to the bottom. Now, you can, of course, put any surface on the bottom. You can put different surfaces on the top, but you don't need to change the glass slide because you need hydrophilic slide here, and typically you want to see what is going on, right? Good question. And the very simple thing that you can use to deposit any particle suspension on any surface. And we have used it in so many other applications, from latex particles to metal nanoparticles. I'm going to show you some very cool anti-reflective coatings, lots of cool stuff. But now the original work was on the principles. Any other questions here? Okay. So now you are a graduate student and you say, well, you know, I know what happens, but now what do I do in order to make this observation into a paper, right? So what do you have to do when you have something like that? What is your next step in writing that is preparing a material that would be paper quality material? What do you do? Kind of like, what is the next principle of obtaining data, right? What should your data look like? I have gone through this process with most of you already. First, you try out something that works, right? Then what do you have to do in order to make a paper?
Do you have to be able to model it and explain it with theory?
Eventually, and yes. But before you model it, you have to have data to model, right? In order to have data to model, you should have what?
Repeatability.
Yeah, even before repeatability, what I mean is the following, right? What I'm trying to show here.
What, you plot it on a graph or something?
Aha, yes. So you should start with one parameter, and then you should have another parameter that depends on this parameter, and then what dependence you get. And then once you get that dependence, then you can make a model. So if you find some parameters that are very simple, that is very simply correlated. So the best models that you can make, of course, we have like in our modeling faculty and colleagues, and they like to make it complex, right? If you want many people to appreciate your paper, you should try to find parameters where you can make a very simple model which captures the physics, and as I'm joking, is no more than 2-story high, meaning that you kind of really should not have more than kind of like essentially a few parameters which are divided and multiplied, maybe integrated. But if you have something which is very complex, then people are not going to be using it because it's complex to use. So Brian's paper was very efficient because what we did with him was the following. You can say, so now I can vary the particle volume fraction, that is how much particles I put here in the meniscus, and I can vary the withdrawal rate of the plate. Both of those are very simple to adjust, right? I mean, like one is down in the syringe pump, the other one is how much you dilute the latex. And then notice that this is not a dependence necessarily, because you're going to have the position of coating at any conditions between those two. You can have any withdrawal rate and any particle volume fraction. Now, again, I want you to kind of be intellectually engaged in what I'm telling you. So imagine that you start with some suspension and you have a small volume fraction and fast withdrawal rate. What are you going to get here? So this is more like a phase diagram or operational phase diagram. What is going to be the type of coating that would deposit here?
Where? Could you repeat that?
On this, here on this side of the graph, right? So high on this axis, low on this axis. So you draw fast dilute suspension. What are you going to get?
When you draw, when
Fast,
you draw too slowly, you're gonna have multi-layer.
Yes, so you're going to get multi-layers here. And Lillian, you may have seen some device like that. I think you want to also use this method, at least for some applications. Alex,
Yeah. Yes,
right?
yes, we did.
Yeah. So monolayer here, what do you get here?
Other way around, right? The
So what
monolayer.
is the other way around?
Multi-layer.
Well,
Multi-layer is here.
yeah, the
Monolayer.
monolayer is when the withdrawal rate is high.
And what if it is higher than that?
Then you have void.
Yeah, so that is called submonolayer, right? You're going to have voids. You're not going to have uniform layer because the particles would collect by capillary forces, but you're going to have submonolayer. So essentially now you can say, I'm going to write the dependence, take the dependence which was derived earlier, volume fraction, withdrawal rate, and so on. You have the thickness of the layer. I can just geometrically connect those. So now when I get the data, I'm going to have the correlation between the volume fraction, the withdrawal rate, and the type of structure that I'm getting. I have one very simple formula which describes it all. It is very simple. I can just use, I have this parameter K here, which I can fit on the basis of the monolayer, and this is the fit, you get pretty good fit. Theory works. So now we have one theory which describes all the type of structures that you're going to obtain here. Once you have this theory, you can say, if I have that many particles and that withdrawal rate, this is what I'm going to get. Here I'm going to get submonolayer with that many particles per unit area, but it's not going to be a complete layer, right? So now then what Brian did was you can even correlate them in a simple way. The thickness of the layer is proportional to the withdrawal rate. So you can have essentially, you just fit the blue curve here, and then all the other curves are kind of like, I mean, describing the type of structures that we are getting. So I hope that you can see, again, this is engineering education, if you will, how you control parameters in coating. Once you know that, yeah, you have something that is very useful. Then you can use it in many other applications. And I'll discuss some applications a little bit quicker next. But let me see for questions or comments here. This is kind of some basic stuff, which may be important. Anyone? Okay, so you can deposit those. Structures. What can you make out of it? So over the years, we have been doing lots of work. So these are just some of the examples of the things that we have been doing. Colloidal crystals, the kind of like the beautiful colors which comes from the organization. Metal nanocoatings. I won't be discussing that, but this was a very kind of like at one point favorite topic, right? How do you make artificial metal conductive coatings? You can make surface enhanced Raman scattering substrate, which is reverse Opal coatings. I'm going to tell you about anti-reflective coatings, which are cool. We have at one point deposited virus and ferritin just for the fun of depositing organic material. Then we had a project with my colleague Michael Flickinger on depositing cells which were producing hydrogen. And then if you put this in an environment where you shine light and you give them nutrients, you may be making artificial leaf that produces hydrogen. So you can have a variety of applications of similar coatings. I'm going to show you some of those, review some of those. They may be useful in your research as well. Any questions here or notes? Know that also these are particles which can start from something which is as small as 10 nanometer protein and can be as large as 10 micrometer particle, right? Anything would be deposited by this method. It has only one disadvantage if you want to do it on a practical scale, which is like what? Can you make this a commercial method easily or no?
There would be an issue with mass production. You can't produce scale up. Maybe. Yeah,
scale up is tricky. The reason is that in usual deposition of coatings, what people do is essentially you have a material has to move very fast, right? If you have a factory, you want to deposit, let's say, a layer of something, you want to have hundreds of meters per second, maybe deposition. In this case, you have to wait for the particles to dry. So it is not that easy to scale that up. Actually, again, you want to have a project, I think, kind of icon together with some people in Lehigh on how to scale that up, but it is hard. But for research-wise, it's an excellent method because you can throw it all and you have a variety of structures. So here is an example of a structure that we had quite a bit of research with a graduate student called Daniel Kunsitsky. This was actually funded by the Army for making surface enhanced Raman scattering sensors, where you want very high metal surface area, right? So how do you make a very high metal surface area with very open structure? You mix it with latex particles, and then after you form the gold structure, then you remove the latex. So this is an inverse metal opal, but it is only this thick, right? You can see it all. You can see all the coating after this, the latex particles have been removed, but you can see where the latex particles have been, and you can see the gold nanoparticles around them. You can actually see the gold nanoparticles. So this is very good. If you shine light on this, you're going to have strong plasmon in that structure, and it can be used for sensors. So that's how you make a thin metal coating.
So the white stuff is
gold
nanoparticles?
Yes. So this is gold.
What the black ones are
the
void?
bottom is glass. What you see on the bottom is glass. You can actually see the gold nanoparticles here, right? That's how they have organized around the latex.
Mhm.
So the usefulness of this is that you have a layer of gold, which is very open and extremely high surface area, and the gold nanoparticles are having the open area of the gold nanoparticles create plasmons, as you kind of like, have heard from different classes, including mine. So this is a gold surface. If you put this in water, you're going to have very high mass transport to a very high surface area of gold. And then if you have, let's say, contaminant or chemical or toxin in water, it is going to on the gold, and then by measuring the surface plasmon, you can detect the material. That's how the sensing works. But essentially, this is a very thin layer of very high surface area gold nanomaterial. And
How thick is this then? I see 14 millimeters. How thick is this layer now?
No, this is 100. So this is 100 nanometers here. See, this is this bar.
Thickness.
No, the bar here is 100 nanometers. So these are 20 nanometer gold nanoparticles. And the thickness of the layer in this case is, I think, probably would be about half a micron or something like that. This is 1 micron particles here. You can see 100 nanometers, maybe even less than a micron, right? So 1 micron from here to here, half a micron down, because this is less than a monolayer.
Okay.
So this is how you make. You can say, oh, but I can make a very thin layer of gold by metal deposition, right? You can do that, but then you're not going to have the high surface area. You're going to have a layer of gold. Even if you put, people have been doing this through latex or silica's template. You can deposit gold here, but then you're going to have a very thin layer of gold, but it doesn't have this high surface area, which is very useful in this case, right? Makes very strong plasma. So this is one application. Another application, we have been doing the so-called coffee ring, which is, again, coffee ring is something that I have seen, heard it over and over and over, kind of like, people being fascinated. The original story of the coffee ring came up later, it was essentially related to our convective assembly. The coffee ring was first described by some people at the University of Chicago. And the journalists were so fascinated by that story. The journalists did not care when we reported the convective assembly, which is the physical mechanism, but they cared a lot when those folks at the University of Chicago reported the coffee ring, which is essentially what happens with that phenomena if you have a droplet and if you have organization of particles at the periphery of the drying droplet, right? So if you have a contact angle, which is kind of like in this case fixed, so you have no slip of the contact angle, the particles will be accumulated because the evaporation takes place here. If you let the droplet shrink, then it is going to compact itself into a smaller droplet, and the particles would eventually form larger particles. But if the droplet is stuck, it cannot move on the surface of the plate. This is, as you know, called contact hysteresis. Then you're going to have contact angle. The journalists were fascinated by that because somebody had described theoretically what happens when you spill coffee and why does it form coffee rings. So this is something that if a journalist relates to you as everyday science, because journalists like coffee and don't like stains. So now somebody explaining them coffee stains has been, for them, it was the big science ever. And it is still kind of like, like coffee ring, people like it. It's a good story. It's a kind of like cool stuff. With Daniel Kuncitsky, however, we described what happens if we have constant angle. And by the way, if we had described the coffee ring, we would be known for the coffee ring. And we have done papers, but like the original story from the coffee rings comes from somewhere else. Another kind of way of thinking of that is if you describe your research in simple terms, so people can understand how it relates to them. Then people get fascinated, and journalists follow and so on. Latest example is the paper of Tamogna about the interfacing, because if you tell them that you can put something on the skin and measure for a long time, journalists like that, right? They understand what, right? So you should try to explain your research in simple terms like that. So we described again, this is another way of drawing operational phase diagram, contact angle, particle volume fraction, and describing essentially everything that would happen if you start depositing the particles in droplets on surfaces. Here it's a kind of like a variety of the structure. You can have a coffee ring, or you can have a particle, single particle, which is going to have also here this kind of like contact length. The reason we were doing this with Daniel was because we wanted to deposit what we're calling pancake or hamburger particles. So essentially, this is an example of a hamburger, which has been deposited by mixing gold and latex and then controlling the contact angle. So you deposit this patch, which is very good for sensing, right? If you hit it with a laser beam from here, you're going to have like, exactly the right size and thickness to make a very good surface Raman scattering sensor. This is a very small particle that you can deposit on surfaces. And then we have lots of fun with Vinayak Rastogi, whom you may have heard, kind of one of our mid-range group members. He's presently in Silicon Valley together with a few other former group members, as you may have heard. He has been working at this time in my group. He has been working on deposition of the so-called opal particles. So what you have here is essentially you take a droplet containing latex and you dry it on superhydrophobic surface. Again, this is a very simple idea. Now it's being used by many people. We tried it with Vinayak, kind of like came up with this cool stuff. Lots of publicity at that time. How do you make those small balls which have these beautiful colors? If you check out Vinayak's paper at that time, you can find out, actually we have described where you see those beautiful rings, right? Colorful rings. We have actually described at what conditions you get those rings. You see that they vary depending on the size of the particle. Here, the rings are emphasized because of the gold nanoparticles in the structure, but you can see that the diameter, so you have one ring, small ring, 2 rings, 2.5 rings, 3 rings, and so on. So we have described this in the paper related based on the Bragg diffraction formula. In this case, this is a kind of a coffee ring combined with drying droplet. So essentially, you have the formation of this donut-like particle, that's what we call them. The donut forms because there is not enough latex at the end because all of it is dried out here. So you can have donuts, you can have glazed donuts, you can have all kinds of cool particles in this way. This research was continued later on in Germany with a guy called Marcel Sperling. He was a German graduate student. I was his co-advisor in Technical University. While I was working with Marcel, I met another guy who I think most of you know, and he's a professor in US now, like some of you have worked with him actually, like Nidhi. So Bubnish was a graduate student at TU Berlin when I was working with this other graduate student on similar particles, and Bubnish and I kind of started finding lots of common interests, and then he joined my group as a postdoc, and now, you know, he's a professor at LSU, right? Okay. Any questions, comments here?
Yeah, I have a question. So when the droplet actually shrinks, like what is causing this formation of the hole at the center? I mean, like it's just shrinking, right? I mean, what is...
Yes, but it's the balance. So the balance essentially, if the droplet has a contact angle, this kind of describes what goes on. So this is essentially the same case, but with the contact angle. If you do not have a contact angle, the same thing is going to happen, but you're going to have a particle which is, I mean, it's going to be self-sustained, right? This essentially, this is half a part, the formation of half a part. When you have a contact angle, you can say, oh, well, I have the droplet, half a droplet, right? It's half a sphere and it forms half a particle. If we have a superhydrophobic surface, it will be a whole droplet, but it's still going to have the same phenomenon. So depending on how the spreading out of the droplet, you're always going, you can have the case where you have enough particles to fill the middle here, right? But if you do not have enough particles, if you have very little particles, they're going to have a coffee ring. They form a coffee ring. If you have lots of particles, they're going to fill up everything completely. If you do not have enough particles, so you're going to have the formation of this thick layer around, and then by the time it reaches here, suddenly there are no more particles to fill up that hole, right? Because all the particles have been transported laterally and have been deposited here. So suddenly the last liquid that can evaporate from here finds out that there are no particles because the particles have been dragged to the periphery. So this is why I was saying that this is like a coffee ring in self-contained droplets on superhydrophobic.
Okay. Okay. Yeah.
Marcel actually later in Germany discovered a number of other particles. If you put this on surface with corrugated surface, then you can control also the one additional directional assembly. So you can have the formation of all kind of bolt-like particles and all kind of other cool stuff. So you could have bolt-like particles, and then we put catalytic particles in those bolts, and then we put the bolts on hydrogen peroxide, and they move around and so on. So you have had some kind of hydrogen peroxide motile particles, which you are saying, well, we don't do hydrogen peroxide, but we have had some German. Anybody else? Okay, so just a few more examples here. Actually, what I'll discuss next, and I'm not going to go through all the formulas, but you can have those slides, and we can have the recording. So essentially, something that I have been doing as a graduate student when investigating foam and emulsion films is correlating the color of the film. In reality, you don't use color light, but use monochromatic light of a certain wavelength, and you just measure the intensity. If you use polychromatic light, which is the usual white light, then you're going to see beautiful color because you're going to have interference and diffraction in thin film at different conditions as the film thins, right? This is foam film, and it is very thin film, very thin here. It is so thin that you do not have reflectance because all the light goes through practically. Here you have this colored film because the yellow light is the white where you have the condition for doubling that is kind of like the bright occurrence here. So this is positive interference, this is negative interference, and the color here changes because this is a foam film in gravitational conditions, so you can see the thickness change. I am not going to discuss all the formulas, so you can see those formulas and you can say, I just saw this earlier. This looks like the Bragg diffraction formula. You can correlate, you can use a formula similar to the Bragg diffraction and correlate the intensity that you're measuring in reflected light to the intensity that falls in. So essentially I0 is the intensity of the falling light. REC, that is the received one by the detector, is the one that is reflected. You have a certain parameter here which relates to the structure of the film, and then you have the delta here, which is a parameter which includes the thickness of the film here. So essentially, depending on the film thickness, you're going to have different color. So now, kind of a little bit of, again, a little bit of something for you to kind of like demonstrate quick thinking. This formula, I said, is similar to the Bragg diffraction formula that we just mentioned. There is one important difference between this formula and the Bragg diffraction formula. This formula has something which the Bragg diffraction formula does not. What would be the case? What is kind of in the formula, which is not in the Bragg diffraction formula? So we have this is a thin film. So this is a thin film of foam film, that is water. But this is the same film that is going to, if you deposit a very thin polymer film, and I'll show you those beautiful films. You have seen all the covers that we have and the awards, the beautiful kind of like image awards that Sabine Islam has received of her polymer films that have color, right? What is the difference between the formula for the Bragg diffraction and the formula for the color of a thin polymer or foam film? There is one parameter that is present in one case and is not present in the other case. That's like a question for Austin, I would think. He's over.
Transmission?
Okay,
So the transmission, in the other case, it's reflected, but in the thin
well,
film
but the
light,
phenomena are the same, right? I mean, like you can have transmission and reflectance here, but for reflectance, the formula looks almost the same, but there is one parameter is present here and was not present in the other case.
it's a refractive index.
Yeah, you like that parameter, right?
I love it. It's my favorite.
Yeah, depending on whether it can be fitted or not. Anyway, so the point is that if you measure the reflected light here, you are going to measure something which is a function of the thickness and the refractive index. So if you change the thickness and the refractive index, you have two means of changing what is going to be reflected from the film, right? This is very important because this relates to the optical properties of polymer coatings, and this is obviously important and to studying similar phenomena. I will kind of go through the formulas here. You can check them out later. The thickness at which you're going to have positive or negative interference is described here. You're going to have, so this is a periodic function because many thicknesses have the same light intensity reflected, because you can have positive interference. So let's say you can have one wavelength difference of the path, two wavelengths, three wavelengths, and so on. The efficiency of reflectance decreases because as the film gets thicker, you have less coherence, you have more kind of scattering and so on. So the kind of, you can do this even only if the film is very thin, right? So it should be, in this case, this is a foam film, but you can see that it can be like, I mean, you have 200 nanometers, 500 nanometers, and so on. This is very good because you can measure very thin film just by measuring their color. The harder way to do that is, again, that will be a question for Austin, is essentially characterizing everything for a thin film by using a device called,
ellipsometer?
Huh?
An ellipsometer?
Yes. So ellipsometer is a device which, if you know the refractive index, you can characterize all the properties of the film, right? So you are kind of reverse using the ellipsometer, so measuring the refractive index of a film. But the idea of ellipsometer typically goes the other way, right? So if you do this you can also determine the polarization and so on. We won't go into those details. If you have a thin bubble pressed on the surface, this is for water again, you're going to see you may have seen these rings. These are called interference rings. If you use those interference rings, you can measure the contact angle. This is used in measuring contact on films. It's a very well-known phenomenon, kind of used for many applications. If you use the formulas from the previous slides, you can calculate the profile of the meniscus here. This is a paper which was written by guess whom? And this was a drawing made by, again, guess who?
You?
Yeah. But notice that this paper is, I have the camera right in front here, 1997. So three-dimensional drawing software was not that readily available then. But still, kind of, if you want to illustrate your paper, you have to make it 3D, right? We have been discussing this. So I'm kind of preaching to the choir here, but you can see that when I was a graduate student, I would draw things in 3D, right? Because if you want good illustration, that's how you make them. This is an example of foam film. This is the stages of foam film formation. It kind of gets to be, this is called dimple, then it gets thinner, breaks down, that is eventually becomes a black film, very thin and breaks down. We're not going to be investigating such films with many of you, but then this one interesting phenomenon that relates here is called anti-reflective. So what are the conditions when you're going to have the least reflectance from a film? Why do you want that? Because you want to make anti-reflective films on different surfaces. If you plot thickness, this was again from Brian Prevost work. So I plot thickness, you can have volume fraction of particles. The volume fraction is going to control the refractive index. So you have thickness, refractive index, and then the transmittance. So you're going to have maximal transmittance if you have the right thickness and the right refractive index. This is how you make anti-reflective coatings. If you take a regular glass surface, glass reflects about 4% of the light from one surface. So if you have a glass, in any glass, if you let light go through, you're going to lose, as transparent as it seems, 8% of the light are not going to go through that glass, right? 4% on one surface of the glass, 4% on the other surface of the glass. So you're going to have 8% of the light is always going to be reflected regardless, right? There is no completely transparent glass. The only way that you can make it transparent is deposit a nanocoating of a certain thickness and a certain refractive index to match those criteria. And if you deposit it right, then you're going to have all the light go through the glass, which is how you make anti-reflective coating. Any questions or comments here? Okay, so how do you make those coatings? You take the cheapest, simplest particles that you can do because you want cheap and simple particles. You take silica, you take silica particles. They are dime a dozen. You don't need monodispersed particles. You don't want color. You want to make an anti-reflective coating. So you take monodispersed, you take polydispersed particles, cheap kind of, you can coat like, the surface of all the glass in the building for 5 cents, essentially. You make those silica particles of a certain coating. You are going to control the thickness, but your refractive index is not going to be controlled because the refractive index is always going to be the refractive index of closely packed silica particles. So you are half the way there. You can control the thickness of that coating. What can you do next to control the refractive index? How do you control the refractive index of such coating? What would be ideas in that regard? Let's see whether you can match what we did at that time.
Change the fluid.
No, the fluid is evaporated, right? So you have particles, silica, deposit them, coating, liquid evaporates, you only have silica layer behind. If you use this method, you can deposit monolayer or thicker layers or very thick layer. You can deposit a layer of any thickness, but it is going to be close packed, so your refractive index is going to be the refractive index of close packed silica particles. How do you control that refractive index?
Can you do that by changing the wavelength of the incident light?
Yeah, but you want the wavelength which is about the middle of the wavelengths of the regular light, right? So it is a little bit of you're matching the light to the coating, but usually you want to solve the other problem, right? You match the coating to the light, not the light to the coating.
Modify the surface of the particles.
Yeah, and so what? You can do that. That will be one hard approach. If you make them aggregate, you can have aggregates which are going to get different refractive index, but you can try something else. Actually, there are a few solutions to that. Any suggestion before we show the 3 solutions on the next slide?
You maintain the same thickness, right?
So the thickness you control, right? So right now, so you need to control the refractive index. That is, you need to control, if you take a look here, volume fraction. Right? You need to control the volume fraction of the particles in that coating. How can you do that?
The size of the particles? With smaller particles have tighter packing?
I do not agree too much with that statement, Austin, because packing of spheres is always the same, right? Regardless of the size of the sphere. You have to disrupt the packing.
I guess less polydispersed. I don't know. That kind of breaks.
Yeah, this goes in the right direction. So, they want to finish in reasonable time. So let me kind of show the 3 ideas that you can do. How do you change the refractive properties? That is, in this case, the refractive index of a column. So first of all, you can put some particles that are going to be temperature particles, fewer particles that are going to be there removed. So you can essentially mix, let's say, latex and silica, then burn out the latex, and then it's going to be less dense. If you take very large particles and you get them to be right, you can maybe control the properties, because now, depending on how you look at this is not the cause pack coating in 3D, right? It's cause pack coating in 2D, so you can go between 2D and 3D. But the simplest thing that you can do, on which we have done at that time, was essentially you take bimodal particles. So you take large and small particles, and by mixing them a different ratio, you're going to determine the essentially the density of that coating. And And you can see here. And they don't need to be monodispersed. So you essentially buy 2 cheap silica particles, mix them in the right ratio, deposit them, and suddenly you have an anti-reflective coating, which is pretty good. That's how it works. And here is an example of what you can do with that. So what you're seeing here is a glass plate. It has been, so this part from here on has been coated on both sides, and this part has not. Now, when you look through the plate, you can see that it's completely transparent plate, right? You can see NC state on both sides. And then if you shine strong light, 8% of the light is already strong enough, so it blinds the camera here. But then there is no reflected light here, so you can still NC state. You can see a little bit of color because this coating is going to be optimized for certain color. So the blue color here is not that optimized, but otherwise you can see pretty well. And again, this is dirt chip coating. You can take that coating, you can deposit it on solar cells. This is a characteristic of a solar cell. We got a solar cell from a company that produces solar cell. That's another interesting story, which you can remind me at the time when we can get back to drink beer together. So kind of, we have to keep this in memory for a while. Remind me the story about the improved solar cells. But if you take the solar cell without coating and then deposit our coating on top, so suddenly you're increasing the performance of the solar cell by about 8%, 10% maybe, which is a lot, right? I mean, if you think of how much more electricity you can get this way, that's very cool. Not that we have worked with solar cell too much, we just demonstrated that. Later on, at one conference, I saw some guys from Germany, that's many years after we published our papers, who said, oh, we came up with something very cool, making anti-reflective coatings of solar, anti-reflective coatings for solar cells out of silicon spheres. And we have a patent, so we are now making this big factory in China for anti-reflective coatings because we have patented that. So I kind of like, I mean, not want to disappoint them to tell them that we have published this many years ago. And if they have a competitor, then their patent is not going to be valid because they did not read the literature and find our paper, right? So they thought, oh, we have come up with something so cool, we're going to patent it and open a factory in China, which they did. And of course, we're not producing solar cells, so we don't care. But other producers who find our paper, then can use the same technology. And these guys would not be protected. So for those of you who write invention disclosure, that's a good thing to have in mind, right? If you miss something, your invention is not going to be validated if you do not describe something that's a background work. We have not patented that, we did not care that much, it was academic work, but kind of this is an interesting story from another perspective, right? Let me check for questions or comments here. Okay, I only have a few more slides to show you. So you have seen some of applications of that work with one of the group members who most of you have known very well and have interacted, Sabina. So this is an example now, if you know what you're doing. So now you can deposit a very thin nanoscale polymer film. And then the uniformity of this film is essentially shown in the blue color. So this blue color is structural color of the polymer film. It's a polyester film. You can drop droplets, and if you drop a droplet, the droplets, because this is soluble polymer, so essentially you want to make coatings out of polymer. The typical way of making nanocoatings out of polymer is dissolve the polymer in organic solvent and then dry it out of the organic solvent. This is not good because the organic solvent then is going to evaporate and typically goes in the atmosphere, and then it contributes to global warming and contamination and ozone and bad things. So you say, okay, so I'm going to replace the organic polymer, the organic solvent with water. But then the problem with those films is that you have to find a way to enhance their, that is, decrease their solubility, because if you deposit the polymer out of water, then it is going to be susceptible to water damage, right? If you have a rain on top of it, each water droplet is going to damage the film. So this is the damage of the film that we described with Sabina. You can see that essentially what happens is the water comes, disperses some of the polymer, and then when it dries, it redeposits it. So it makes coffee rings. So essentially the polymer, I'm going to play this again. So the polymer stops being covered because you have a thick droplet. And then it dissolves the polymer and then redistributes it in the form of a coffee ring. So this coffee ring, essentially, so you can see here thicker area and then thinner area, right? So this is blue, thicker area is yellow, and then this thinner area, in this case, is blackish. It looks brownish, but it's kind of like an inverting film, right? So essentially, you have damaged the film because you have a coffee ring damage. This was described in Sabina's paper. Essentially, the model for how we do those, essentially the different types of modes of damage and how it relates to solubility. This was a paper that just came out this year and, of course, had another journal cover for obvious reasons here. This is how essentially you relate, hopefully, all the stuff that I was telling you previously to different types of optical properties. We have been doing this for quite a while. I had a few slides which relates to the wonderful properties of the dendrimeric particles and coatings that we make. But this is something that Austin can tell us during our next group meeting. So I'm going to kind of finish here basically, and maybe have a moment for questions. I hope that some of you guys may be interested in asking some questions about these coatings and other related topics. So we can finish this educational lecture. I hope that this has been useful. We're going to pause that recording so you guys can take a look and maybe this can be useful for many of you, regardless of the type of research. You may need to use coatings. You may need to understand the coffee ring phenomena, evaporation phenomena. So hopefully this has been a good introduction to some of those topics. Let me check for some questions. Anyone?
Sorry.
I assume that many of you will can use those methods. I mean, you have seen as I'm joking, the high-tech device out of the syringe pump. Again, one of the take-home messages from this lecture for you would be that, and you have heard me mention this many times, you do not need to make something that is very complex in order to make good research, right? So we want to, of course, have everything that is needed for your experiment to go, but you designing some very complex experimental setup, in many cases does not pay off, because as long as you do it smart and you do some new stuff, you can publish some good papers and people are going to like them. Any final question? Anybody something nagging you about what I showed you? The phenomena, description? Well, okay. If not, I think that this has been going on for quite some time. I have piled up lots of information. I'm going to send you the slides around for your information and reference. But hopefully this has been a good introduction to the topic. Again, these are useful things. We're going to continue with our next group meetings. In the meantime, as I mentioned,